Studying many masses on springs, each undergoing simple harmonic motion, is an excellent way to understand how waves move through a medium. We call this wave propagation. Here you see a simple example in front of you. I have three masses connected by springs, and what I'd like you to do is imagine that those masses connected by springs, they simply go off to infinity in both directions. Now, waves always propagate parallel to the springs in this model. The masses themselves can move either up and down or left and right as they vibrate. When the masses move back and forth in the left-right direction, this is the same direction as that of the propagation. The wave is said to be longitudinal. A good example of a longitudinal wave is a sound wave in the air. On the other hand, when the mass displacements are at right angles or perpendicular to the springs, the waves are said to be transverse. Examples of transverse waves include light waves and surface water waves. Here is an example of a displacement of a transverse wave, and you can see the propagation direction directly at right angles to the displacement itself. Now, what I'd like you to do now is imagine in your mind's eye adding more and more masses to our masses and springs model. Make the masses closer and closer together, and they weigh less and less and less individually, but we keep the tension the same. Well, what we're doing then is taking our masses and springs and turning them into, in effect, a continuous string. Now, a string helps to remind us that waves involve not just periodic, simple harmonic motion of each of the local bits, but a wave also involves periodic structure in space. So how can we understand both of these ideas at once? Well, if we look at one particular location on the string as the wave passes, we observe that the displacement, let's call it d of t, is just a times cosine omega t. A here is called the wave amplitude. And in case you're wondering, if I chose d of t equals a sine of omega t, that would work just as well. Whether it's a cosine or a sine, it just depends upon the precise moment that you choose to call t equals 0. Now, if we take a snapshot at one particular time and choose our origin, x equals 0, so for a cosine that would be the peak, then the string displacement in space takes the form d as a function of x equals a cosine of some constant k times x. Now, a is the amplitude just as before, but k is a new constant. So to understand what k is, remember omega. Omega, when we studied the time behavior, was 2 pi divided by p, the period of simple harmonic motion. Now, when t advances from 0 to p, then omega t is omega p, and that advances by 2 pi, and cosine omega t completes one full cycle. So let's take our k and we do the same. So let's take k and do the same. set k equal to 2 pi divided by lambda, where the Greek letter lambda is known as the wavelength. When x advances from 0 to lambda, so that kx is k times lambda is equal to 2 pi, that corresponds to one full cycle of the wave cosine of kx to be complete. Not in time, but now in distance. You see on the diagram in front of you one wavelength, the distance from one peak to the next. Now, of course, we can take any starting point, let's call it x, it doesn't have to be the peak. When we add lambda to x, our starting point, we arrive on the wave cycle exactly where we started, at the same phase. Now here is a function that can make a wave both in distance and in time, all at once. We'll write it d of x and t equals a times the cosine of kx plus omega t. Now, notice that if we fix the time at some particular point, let's call it t star, then this displacement is just a times the cosine of kx plus omega t star. Well, that's just simple harmonic motion in space with an unimportant phase constant, omega t star, which doesn't affect the wave-like properties at all. On the other hand, if we start with the same d of x and t, and now we fix x at some particular point, x star, then the function, the displacement, is just a times the cosine of kx star plus omega t, which is simple harmonic motion in time, again, just with an unimportant additional phase constant of kx star. The plus sign in a cosine kx plus omega t, that doesn't matter. Cosine of kx minus omega t would work just as well. So here you see an explicit graph of a cosine of kx. And I've chosen t equals 0. Now, if we look at that wave a short time later, let's call it a time t1, then cosine of kx plus omega t1, as you can see, has moved a little bit to the left of the original wave in purple. And if I look at a still later time, t2, the wave has moved yet more to the left. This is cosine of kx plus omega t2. Now, let's go the other way. Here is our original wave, cosine of kx. Cosine of kx minus omega t1 has now displaced the wave profile to the right. And similarly, at a later time, cosine of kx minus omega t2 has displaced the wave yet further to the right. So what is happening here? Let's look at the second example, cosine of kx minus omega t, and let's start at x equals t equals 0. This is clearly a peak. Now, as it moves, this peak must always keep the combination kx minus omega t equal to 0, or it wouldn't be a peak. So at some time t, let's call it delta t, where has the peak moved to? Well, it must have moved to a position that we call delta x, where delta x is given by the requirement k times delta x minus omega delta t is still equal to 0. Well, that's an easy equation to solve. delta x is omega delta t divided by k. And here you see it shown explicitly on the graph through the red arrow showing the motion of the peak. So delta x equaling omega delta t over k is needed in order for the wave to keep the peak at the same location, the peak, as it moves, with cosine of 0 always equal to 1. We can solve this equation by dividing both sides by delta t, and we find that delta x, the distance that the peak has moved, divided by delta t, the time it took for the peak to move, is simply omega divided by k. This must be the velocity of the peak, or for that matter, the velocity of any part of the wave profile. Let's do the same thing now with cosine kx plus omega t, once again starting at x equals t equals 0. In this case, we must have k delta x plus omega delta t equals 0, and that leads to delta x divided by delta t equaling minus omega k. This is the velocity of the peak or any other point of the wave profile, but now moving in the negative x direction. And you can see that clearly in the motion of the cosine wave, which I've plotted here for you in the form of the displacement shown by the red arrow. In other words, in one period p, the wave peak, or any other part of the wave profile, will have moved one full wavelength. That could be in either direction. Well, the velocity associated with this, distance divided by time, is lambda the wavelength divided by p the period. And if I multiply by 2 pi and divide by 2 pi in that expression, that is equivalent to omega over k, just as I found before. So the easiest way to remember the velocity of the wave is simply lambda over p, or, because p is 1 over the frequency, f, the frequency, times lambda, the wave velocity, is equal to the frequency times the wavelength. To recap, what we have shown here is that waves consists of sines and cosines of the combination kx minus omega t. Omega is the angular frequency, k is called the wave number, and it is 2 pi over lambda, the wavelength, just as the angular frequency omega is 2 pi over p. If we know the frequency of the wave and we know its wavelength, we simply multiply the frequency times the wavelength to calculate the wave's velocity. What we'll do next time is to take this result and apply it to an understanding of sound waves.